Welcome back. We are going to be looking at our momentum notes. These notes shouldn't be too long. It's a fairly short unit. So let's get going. The first thing we talked about was momentum. And we said that momentum is inertia in motion. And remember we said that inertia is being stubborn. So it's something in motion and it's stubborn. So that means it wants to stay in motion. So things that have momentum are moving and they want to keep moving. They don't want to stop. So if something has more inertia, it really wants to keep moving. If something has more momentum too. If something has a lot of momentum, it's on a roll, it wants to keep going. Little momentum means it's easier to stop it. The symbol for momentum is P. Why P? I have no idea. M is for mass, so M can't be for momentum. So P is for momentum. And the units are kilogram meters per second. And that's just what it is. It's kind of complicated and ugly. And I'll show you an easy way to remember that in a second, after I show you that the equation for momentum is mass times velocity. And so because P equals mv, if you ever forget these units, you can always think of the units for mass as kilograms, times the units for velocity as meters per second, and kilogram meters per second is the same. It's the units of momentum. So that works out very nicely. So let's look at an example. First example, a large truck and a small car are moving at the same speed. And we said the truck has a greater momentum because it has more mass. So this means the truck is harder to stop. So because of our equation, P equals mv, if this first one is the truck, and the second one is the car, call it C, if this m here is much bigger than this m, then the P has to be bigger. You increase m, you increase P. All right. Second example was a mathematical example. What is the momentum of an 8 kilogram bowling ball? So to do this, once again, we highlight what we know. I know 8 kilograms, 3 meters per second, and it's asking for what is the momentum. So what is the momentum? We have 8 kilograms and 3 meters per second. This is a mass, this is a velocity. Our equation, very simple, very easy. Our units, kilograms, meters per second. All right. Oops. We have one more example. We just did example 2. There's one more. It was a think, pair, share that we talked about. And it said, can a truck and a skateboard ever have the same momentum? And the answer is yes. Yes, they can have the same momentum. They could have the same momentum if they're both at rest. If they're both at rest, then V is 0 for both, so the momentum would be 0 for both. They could also have the same momentum if the skateboard is moving a lot faster than the truck. So because the truck has more mass, if the skateboard has more velocity, they could even out. They could even out. All right, now we're on to impact force. We had an equation for impact force. Impact force equals mass times a change in speed. And so we're going to be using this for our egg drop. And we said there are 3 ways to lower this force. If we want this force to go down, we can do 3 things. The first thing to do is to lower the mass. So if we lower the mass, we make things lighter, they hit softer. They don't hit as hard. So the mass goes down and the force goes down. The other thing we can do is slow down. So if this speed goes lower, then the force gets lower. Obviously, if we're going very slow, it's not going to hit very hard. And the last thing we could do is increase the stopping distance. And this one we talked about because this speed has a distance hidden inside it, actually has a distance and a time hidden inside it. If you increase that stopping distance, you are actually lowering the impact force. So we showed this with the egg and the sheet. That the sheet cradles the egg, it goes back with the egg, it increases that distance, and it lowers the force. So the egg won't break. And of course, if we want to increase this impact force, we either need to increase the mass or increase the speed, or decrease the stopping distance. So that way if it hits like a brick wall or the cabinets in my room, the egg would break immediately. All right, elastic collisions. The book said it's collisions where objects rebound without lasting deformation or heat generation. So the objects bounce and they're not deformed. All the energy is going into bouncing them back up. All right, so my one-word definition is bounce. And examples we said were balls on a pool table, tennis balls bouncing. Elastic would also be the gun shooting. The bullets go one way, the gun goes the other. That would be an elastic collision. Jumping out of a boat. If you jump out of a boat, you go one way, the boat goes behind you. So any of those types of problems would be elastic. You're bouncing apart from each other. And there is no deformation. Nothing is deformed after the collision. The opposite is inelastic. Inelastic is a collision where objects are deformed, they get clumped together, heat is generated. And so I said they stick together. So examples of this: clay hitting the floor, dropping an egg, a car crash. These would also be our big fish eating the little fish. These get stuck together. They get deformed when they hit. And so what happens is when they hit, that energy is not going to rebounding, to bouncing. That energy is going into changing the shape of the object. So that's why they don't bounce. All right, conservation of momentum says that momentum is not created or destroyed, but it can change from one object to another. And we said there are many conservation laws. We related it back to conservation of matter, which says matter cannot be created or destroyed in a chemical reaction. You learned about that in chemistry. So this is momentum, same idea, same principle. I showed this with a demonstration with the little cars on the tracks. How if I had one car at rest and the other car is moving towards it, when it hits it, the car that was moving stops and the other car moves at the same speed as the original car was first moving. So the momentum is the same, it just changed from the first car to the second car. We also saw it with the Newton's cradle, the little 5 balls that go click-clack back and forth, and we raised different number of balls up. We raised 2 and 3 and 4, and whatever the momentum started with, it had to end with it too. So after the collision, if we had 3 at the beginning to start with, after they collide, we have 3 kicking back up at the end. So momentum is conserved, it doesn't change. And so the total momentum before is the same as the total momentum after. Not created, not destroyed. It's the same, always the same, before and after. And we use this for this math equation. So what this is basically saying is this is for 2 objects colliding. And this is saying this one is the momentum of the first object before it hits. This is the momentum of the second object before it hits. So we said this is the before side. And it must equal the after side. So this is the first object after it hits, and the second object after it hits. So the momentum before equals the momentum after. All right? And we did say this equation can change. So if I have 2 things that all of a sudden turn into 3 things, for example, if I have a ball that's moving, and it hits um, it hits a scarecrow. This is the before and after. After, if the ball keeps moving and it knocks the head off the scarecrow. Then we have two things before. This would be number 1 for M1V1. This would be number 2 for M2V2. And then for our after side, the ball would still be 1, the body would be 2, and the head would be 3. So we would actually add an M3V3 because now we have 3 objects after the collision. And so we talked about morphing this. Another example we said was with a firework. If a firework has 1 object before and it explodes into 2 objects, then our equation would basically for our equation, we have 1 object at the beginning, so we would not need this term. So we would just have M1V1, which would be our firework. Oops. So our firework would be object number 1 before, and then after, we would have 2 objects. So this equation can change. The equation as it's written, as it's posted on the wall, this guy right here, is for 2 objects colliding. So we have 2 objects at the beginning, 2 objects at the end, but like I said, we can change this up a little bit. And we did say that things moving to the right and things moving to the left have to have a difference. And so we say things moving to the right are positive, things moving to the left are negative, and I said it always helps to draw a picture. So let's look at an example. So Moops and Meeps are at rest, but resting on a frozen lake. Meeps pushes Moops backwards. So we have Moops and Meeps. We'll draw the before picture. Here they are, they're wrestling. I'm going to label them. Here's Moops. Moops has a mass of 10. Meeps has a mass of 8. And they're wrestling, they're at rest, they're not moving. Okay? After the collision, she pushes him, so he goes backwards. And for every action, there's an equal and opposite reaction, so the reaction is she goes backwards because they're on a frozen lake, there's no friction. The masses are still the same. This is 10, this is 8, and we know she pushes him back with a -4. It's going left, so it's -4, and this one we don't know. So when we solve this, we have 2 things before, and we have 2 things after. Okay? So I'm basically going to put the Moops information into the first term. So I get 10 times 0. I put the Meeps before in there. So that's 8 times 0. And then I have the after. And I have the Moops after. That's going in there. And I have the Meeps after. It's going to go right in there. So now the left side just becomes 0, and the right side becomes -40 plus 8b prime. I'm going to add 40 to both sides. So I get 40 equals 8v prime. Divided by 8. V prime equals 5 meters per second. All right, so if you want to see another example of this, I do have a separate video walking through another example. And hopefully you guys understood this. I hope you learned something, and I will talk with you guys later.